Now that we've seen some examples on how to find the eigenvalues and eigenvectors for a matrix or a linear map, I want to give some basic definitions and also talk about some properties about these things. So, definition, the characteristic polynomial of a square matrix A is the determinant A minus x times the identity matrix, where x is just some variable. You could have put a lambda here, it doesn't really matter. And the characteristic equation is the equation, so you set the characteristic polynomial equal to 0. Characteristic polynomial of a map, f from a vector space V to itself, is the characteristic polynomial of any matrix representation of f with respect to a basis B for the domain and codomain, which are the same. Okay, so I could rephrase the process that we talked about in the previous section to just say that to find the eigenvalues for a matrix, you just solve the characteristic equation. You set the characteristic polynomial equal to 0, and the solutions to this equation, this characteristic equation, are just going to be the eigenvalues. And then the eigenvectors are found slightly different. You just solve a minus lambda I is equal to a minus lambda I times v is equal to 0. You just solve that system of equations, and this gives you your eigenvectors. But anyway, so that is our definition. Next I want to talk about a lemma. The lemma says that a matrix always has at least one possibly complex eigenvalues. So if you allow your eigenvalues to be complex numbers, like 5 plus 6 times the square root of negative 1, then you will always have at least one eigenvalue for your matrix. And the proof of that is pretty straightforward. Eigenvalues are literally just roots of the characteristic polynomial. So any root of the characteristic polynomial is an eigenvalue, and every degree at least one polynomial has at least one root over the complex numbers. So like the polynomial x squared plus 1 doesn't have any real roots. By root I mean solutions to setting the polynomial equal to 0. But it does have complex roots because if you do the square root of negative 1 squared plus 1, that's equal to negative 1 plus 1 equals 0. So the square root of negative 1 is a root of this polynomial, but it's a complex root. So as a quick example to demonstrate this, what is the characteristic of this 2 by 2 matrix? Well, I do 1 minus lambda or 1 minus x. It doesn't really matter, whichever one you want to do. Maybe I'll just do x for the sake of it. 1 minus x, negative 2, 1, and negative 1 minus x. This determinant is equal to 1 minus x times negative 1 minus x minus negative 2, which is plus 2. Here I get, all right, this looks like negative 1 plus x minus x plus x squared plus 2. And this is equal to x squared. Okay, so these cancel out, and then I'm also left with 2 minus 1, which is equal to 1. So then the eigenvalues, so you can factor this over the complex numbers to be x minus I times x plus I, right? If you were to distribute this out, you get x squared minus ix plus ix minus I squared, so minus negative 1, which would be plus 1. So the eigenvalues are plus minus I, or plus minus the square root of negative 1 Did I say something wrong up here? No, I just said that I was one of the roots of that thing, but negative I is also a root / eigenvalue for this matrix. Okay, cool. Another definition, eigenspace. So the eigenspace, maybe I should highlight this. Red. So the eigenspace of a matrix A associated with the eigenvalue lambda is, so it's denoted by V sub lambda, and it is the set of vectors, maybe I should say V in V, such that A times V is equal to lambda times V for some non-zero, or actually, sorry, for any V. So here, V is allowed to be the zero vector. That is a allowed thing here. And remember that the zero vector would always satisfy A times 0 equals lambda times 0. So this set in particular is always going to be non-empty, but if lambda is an eigenvalue, then that means that there is a non-zero eigenvector, and so this set would have more things than just the zero vector in there. Oh yeah, and so you could define this for a linear map as well. So instead of defining it for a matrix, you define it for a function v to v. And it's just the same thing. It's just the set of vectors in your vector space. Well, okay. So in here, maybe I should have done v is in Rn so that A times v actually makes sense. Yeah, this is better. This should have been Rn to start with. Now here, this is a linear map f from v to v, and it's the set of vectors in v such that f of that vector v is equal to lambda times v. So it's the set of eigenvectors. So the eigenspace is really just the set of eigenvectors for an associated eigenvalue, and that includes the zero vector, which if it's an eigenvalue, the zero vector will be in here as well as other vectors, other eigenvectors. So anyway, the lemma that goes along with this, so I called it an eigenspace, and the reason for the naming is because it is actually a vector space in and of itself. So the lemma says that the eigenspace is a non-trivial subspace of the vector space V. V could be Rn. If you're doing this for matrices, that's also totally fine. Doesn't really matter. So what's the proof of this? So how do I show that something is a subspace of a vector space? Well, I could just do the subspace test. You remember that, hopefully. So what do I have to do to show that the subspace test holds? So first thing, note that the zero vector is always in v lambda, since I'll just do it for matrices in this case. So A times 0 is always equal to lambda times 0 because both of these are just equal to the zero vector. So it's non-empty. What else? You need to show that, well, all right, so let's let v1, well, I'll say v and w be in v lambda, and I want to show that v plus w is in v lambda. Okay, so if v and w are in v lambda, then that tells me that av is equal to lambda v, and aw is also equal to lambda w. Remember that this is for a fixed lambda, or fixed eigenvalue lambda. Okay. So I want to show that v plus w is in v lambda. In other words, I want to show that a times v plus w is equal to lambda times v plus w. And how do I show that? Well, first I can just distribute here. So this is equal to AV plus AW. This is just facts of matrix multiplication. And AV, we already know, is equal to lambda V. And AW is equal to lambda W. Now I can just factor out this lambda. And this is equal to lambda V plus W. And so that's exactly what I needed to show that V plus W is in V lambda. And then you could do the same thing for, to show that, let's let V and V lambda and R be in R. Then AV equals lambda V. And so R times AV is equal to R times lambda V. And then this tells me that A times RV is equal to lambda times RV. And then that would tell me that RV is in V lambda as well. And that's it. I'm not leaving myself enough space here, but whatever. So yeah, that's the proof. Okay, cool. Moving on. All right, so characteristic polynomial can always factor, right? So let's suppose that we can factor the characteristic polynomial for a matrix A as x minus lambda 1 to the power m1 times x minus lambda 2 to the power m2, etc., up through x minus lambda n to the mn. Okay. So we've seen before that like we could have, so we had like one example where we had like x minus 0 times x minus 2 squared or something like that. So anyway, that's mostly what this is saying. So anyway, we say that the algebraic multiplicity of an eigenvalue lambda sub I is the degree m sub I. And the geometric multiplicity of lambda sub I is the dimension of the corresponding eigenspace V sub lambda I. Okay, so algebraic multiplicity is just like what is the power corresponding to that eigenvalue in your characteristic polynomial. And geometric multiplicity is just the dimension, the size of any basis for the eigenspace. So let's go back to some previous examples that we talked about. So here's one matrix we had. A is equal to 2, 4, 0, 3. This is the one we started with. It has eigenvalues 2 and 3 with eigenspaces given by the following. So V2 we saw earlier was equal to the set of 1, 0 times x for x and r. So this is the span of the vector 1, 0. And V3, the eigenspace corresponding to the eigenvector 3, was the set of multiples of the vector 4, 1. So it's the span of the vector 4, 1. And the characteristic polynomial for this factored as x minus 2, x minus 3. And so, so from there, I can say, maybe I want to be in red. So the algebraic multiplicity of lambda equals 2 is 1, and the geometric multiplicity is also 1. The algebraic multiplicity is 1 because the power of x minus 2 in the characteristic polynomial when we factored it was equal to 1. And then because the corresponding eigenspace was spanned by one vector, then the dimension of V2 was equal to 1, and so 1 is the geometric multiplicity. And then similarly, the algebraic multiplicity of lambda equals 3 is also going to be 1 because we have 1 is the power of x minus 3 right here. And then the geometric multiplicity of lambda equals 3 would also be 1 because it's the eigenspace is spanned by one vector, eigenvector. Okay, cool. The next one we did was this matrix A. So this has eigenvalues 0 and 2. Its characteristic polynomial was negative x times x minus 2 squared. And so we also found that v0 was equal to the span of the vector 1, negative 1, 1, and v2 was equal to the span of the vector 1, 0, 1. So here, so for lambda equals 0, the algebraic multiplicity is equal to, so the power of, so this is equal to like x minus 0 to the 1. So the power of that would be 1, so the algebraic multiplicity is 1, and then the geometric multiplicity is also equal to 1. So this is not so interesting, but for lambda equals 2, what do we get? So algebraic multiplicity would be 2 in this case, and then the geometric multiplicity would be equal to 1. So here in this case, we are getting that the algebraic and geometric multiplicities are different in this case. Okay. Cool. Maybe I want to bring this up a little bit. Doesn't matter. So here's the map that we talked about in the beginning of this section, but I didn't do much more with it. So pi from R3 to R3 sends xyz to 2x, 2y, 0. So pi of xyz, you might note that this is equal to this matrix with twos and a 0 along the diagonal times the vector xyz. You could get this matrix just by looking for the representation of, with respect to E3 and E3 of the map pi, and then finding this map representation the same way that we've been doing. Or you could just notice that you could kind of just I don't know, maybe you can kind of just see that this is true just by looking at this, that this is equal to 2x, 2y, 0. Maybe you can see that. But anyway, so what is the, all right, so what's the characteristic polynomial? So it's the determinant of our representation minus lambda times the identity matrix. So I get 2 minus lambda, 0, 0, 0, 2 minus lambda, and I'll get 0 minus lambda down there. So this is going to be 2 minus lambda squared times negative lambda. So this is negative lambda minus 0 times 2 minus lambda. Or I guess I could write this as lambda minus 2 squared. This is being squared, so I can multiply both of these terms by -1. That doesn't change the sign, so this is still correct, but whatever. Okay, so eigenvalues are 0 and 2, as we talked about in the beginning of the section, but this actually tells us that these are the only eigenvalues. So these are the only eigenvalues. So for lambda equals 0, what is v sub 0 going to look like? Well, I'm looking for solutions to a times a minus 0I times x is equal to 0. So I'm trying to just find the null space of A, really. So in this case, it's going to be, let me scroll. Okay, it's going to be equal to, all right, maybe I shouldn't go fast through it, but, so I'm just setting, so this is already in reduced echelon form, so I can see that 2x equals 0, 2y equals 0, and then z. Z is a free variable. So x is 0, y is 0, and z is free. So this is our v0. So the geometric multiplicity is equal to 1, and so is the algebraic multiplicity. And then for lambda 2, I'm looking for a minus 2i. I'm trying to find the set of solutions to this times vector is equal to 0. And so 2 minus 2 is 0. And then 0 minus 2 at the bottom right would be negative 2. So in this case, I get negative 2z is equal to 0. And then x and y are free. So then v2 would be the set of x, y, 0, such that x and y are in R. So this is the span of 1, 0, 0, 0, 1, 0. So in this case, the geometric multiplicity is 2, and the algebraic multiplicity is also 2, because the characteristic polynomial had a square